You recently released a controversial paper on black holes and how they're more akin to black mirrors. Explain the primary idea behind this result and why it's caused such a stir among a subset of physicists.
What we are explaining is a mathematical solution to Einstein's equations, um, which describes black holes rather differently than the conventionally accepted solution to Einstein equations. So it was motivated by our work in cosmology, where we noticed that the Big Bang singularity is actually not all that singular. And we used a technique called analytic continuation, which is a mathematical method related to complex numbers, a very powerful, very beautiful method, which often works in physics. And we used that method to traverse the Big Bang singularity and find a mirror universe on the other side. So one of my PhD students was bold enough to say, why not try this for black holes? And I myself hadn't attempted it because I thought black holes are a lot more complicated. But sure enough, he was able to get the same method to work for a black hole. And strangely enough, it gave a new and alternative interpretation of black holes themselves. So in essence, the point is that the black hole horizon is a rather special surface in space-time. You should think about it as a two-dimensional surface enclosing the black hole. But if somebody inside emits a signal, we will never, ever receive it. And so you may wonder, is the inside real if we can never receive a signal from the inside? Now, the conventional interpretation is that it is real, and that leads to all kinds of paradoxes. If something falls into a black hole, the information it carries is lost and can never be received outside. And the paradox gets even worse if the black hole evaporates quantum mechanically, as
Right.
Stephen Hawking described, which is widely accepted that black holes will evaporate because this information is then lost forever. And that's incompatible with quantum mechanics. Quantum mechanics doesn't allow you to destroy information. So, and there are other puzzles about black holes. You see, if we watch somebody falling into a black hole, we as outside observers would never actually see them falling through the horizon. What we'd see is that their time would effectively slow down, and anything they were doing, anything they were using like clocks, would just slow down and freeze. And the ultimate picture we would have of them is that they're just frozen on the horizon. And so again, people have wondered, if what happens inside the black hole is never actually observable, is it really true that the interior of a black hole even exists? So we applied this method of analytic continuation to the metric of a black hole. We actually did it for ourselves, or my student did it for himself. But later we discovered that Einstein himself had used the same method before the conventional description of a black hole was discovered by Martin Kruskal. Martin Kruskal discovered how to describe the transition across the horizon in a, let's say, kosher mathematical way, I think around 1960. But even before that, Einstein was puzzled by the black hole horizon. And Einstein and Rosen, the same people, Einstein-Podolsky-Rosen, the famous EPR paradox in quantum mechanics, the same Rosen with Einstein, solved the equations for a black hole in a different way. And basically, they use this technique to transition through the horizon. And they discovered what is called the Einstein-Rosen bridge. And this connects two exteriors of the black hole, which are really distinct universes. And as you follow the solution to the horizon and beyond, you emerge in the other side of the black hole. And in fact, this is absolutely analogous to what happens in our description of cosmology. We go back to the Big Bang and we just follow it through and we come out on the other side and there's another Big Bang there. And it turns out that all known solutions of GR have this form. All known black hole solutions and all cosmological solutions which begin with radiation domination, as ours seems to, they all have this property of the two-sided character. So, but what surprised us is that we found we emerge on the other side without even noticing the black hole interior. Okay. So mathematically, effectively, you hit the horizon surface on one side and you come out on the horizon surface on the other side into the other universe without seeing anything in between. So there is no black hole interior in this solution. Now, that seems strange. Something must go wrong because we've managed to avoid, the singularity. Because in the middle of a black hole, inside the black hole, there's this curvature singularity, which is where the Einstein equations break down. And, if you fall into a black hole, you're going to hit the curvature singularity. There's nothing you can do, and you'll be sort of crushed and stretched infinitely. So the standard description has this severe problem that inside the black hole, the equations fail. That doesn't happen in our case, but something else does fail. It turns out that in the usual picture of general relativity, you have this space-time metric, which you use to measure distances. And in the normal approach to general relativity, that's a matrix. This method is a 4x4 matrix. And one of the axioms is that it must be invertible. You must be able to write down the metric and its matrix inverse. It turns out that in this coordinate system we are using, and which Einstein used before us, Einstein and Rosen used before us, the metric fails to be invertible exactly on the horizon. So it's completely analytic, meaning it solves the field equations, but this one axiom breaks down on the horizon. So we would say we have a type of singularity. It's in the conventional sense of GR. You can't only use conventional GR to make sense of this, but it's much milder than the singularity you would otherwise have if you took the inside seriously. So in other words, we found a way of avoiding all curvature singularities in black holes, which involves accepting another kind of singularity, which is this. Essentially what happens is the metric is not invertible on this surface. Now, is that a catastrophe that the metric is not invertible? No, by no means. There's nothing, God-given that says that the geometrical description, you see, essentially the idea that the metric is invertible can be phrased much simpler by saying that locally, in space-time, if I use a magnifying glass and I zoom in as much as I can, then locally the space-time just looks like flat Minkowski space. There's no impact of gravity at all on short distances. That's the usual the way. And if you say that, then when you zoom in on a given point in space-time, you can always use the Minkowski metric and just forget about gravity. And the Minkowski metric is invertible. So that's the usual justification. So we are saying something special does happen on the horizon, but it's not that bad. Okay. It needs a physical interpretation. What special is happening? Now, the special thing that's happening is to do with CPT symmetry.
Great.
So CPT symmetry is charge conjugation, parity, and time reversal, which basically means that you take the conventional description of it is you take the coordinates in space-time, which we think about as numbers. There's the time coordinate and 3 space coordinates, and you replace them with minus themselves. Now, probably the nicest way to think about this is if, in effect, you are rotating space into time. Okay, so if I think of time going up and space going sideways, you do a rotation by 180 degrees, so time goes down and space goes in the other direction. So that is what do we call a PT transformation? It's parity, reversing space, and T, time reversal, reversing time. Now, in special relativity, you're not allowed to rotate space into time. Okay, we're allowed to rotate space into space because we see that the world is pretty much invariant under rotations in space, but you can't rotate space into time. Why? Because in special relativity, you're only allowed to boost, meaning you can travel faster, and that has the effect of squishing space and stretching time, but you can't actually rotate them into each other. Now, again, this comes into the mathematics of complex numbers. So it turns out that in particle physics, when you calculate scattering of particles or any event involving ingoing and outgoing particles, you are allowed to rotate space into time, and that's a exact symmetry. So one of the most famous, expositors of quantum field theory is Sidney Coleman. And he has this beautiful book. His lectures at Harvard are sort of a classic, and his students wrote them all up. And they're the best place to learn about CPT, by the way. And Sidney says, look, if we discover in an experiment that charge conjugation is violated, when you change a particle into an antiparticle, you discover that physics changes. That's no big catastrophe. If parity is violated, inverting space is not an exact symmetry, that's not a catastrophe. And same for time reversal. The laws of physics we know do actually violate time reversal, space inversion, and charge. Each of them is violated separately. But, he says, if CPT is violated, that is a complete calamity. We would have to start all of physics again. Okay? So CPT is very profound. Now, it changes particles into antiparticles. And the nicest way to picture this geometrically was realized by a guy called Stuckelberg in 1941. And so he was a genius in Austria who was not sufficiently recognized in his lifetime. But he realized that if you think of space and time, so time goes up, space goes sideways, and now think of a particle. What's a particle in space-time? So a particle is what we call a worldline. So this particle is a curve, every particle follows a curve through space-time. So if I slice the space-time in the time direction, I'll see this point moving along in space on different slices, as the slices proceed.
New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, hey Curt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts? While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist.